The last disruption in equilibrium we're going to talk about is change in temperature. So we need to refer to the terms endothermic and exothermic process for talking about change in temperature during equilibrium. Endothermic processes are just processes where heat, symbolized by delta, is added to reactants in order to make products. If I have to put heat energy into a reactant to make it happen, I've got an endothermic process. An exothermic process is when the reaction is happening, heat will be released, leaving a system. The example we're going to do is an endothermic process where I'm going to take dinitrogen tetraoxide, add heat to it, and I'm going to make 2 moles of nitric oxide, dangerous, poisonous gas. It is the sibling of nitrous oxide, which you might know as laughing gas, but you shouldn't get the two confused with each other because consequences would be really bad. So N2O4, which by the way is a propellant that is added to rocket fuel in order to help catalyze the process in order to get the rockets to light and ignite, is a colorless gas. But when I add heat to it, I eventually make NO2, which is this brown gas. So we're going to see what happens with this process as I add more heat. So here we have our equilibrium system where I've got a combination of dinitrogen tetraoxide and nitric oxide. I've got 4 molecules of N2O4 with 6 molecules of NO2. It's in this container. The first thing I'm going to do is I am going to increase the temperature. I increase the temperature. My little Bunsen burner go there. Since it takes more heat in order to get the reaction to go, when I add heat to this system, the equilibrium will end up shifting to the product side. So if I'm adding heat to the left to compensate, I will add more product to the right. And this happens because I have an endothermic reaction. So going back here, so since I added more heat, if I added more heat to compensate, I made more NO2. And you'll see that because the color of the gas that was produced turned a darker brown. So, moral of the story, if I have an endothermic process, the direction that the equilibrium will shift will be to the product side in order to compensate for the heat put on the reactant side of the reaction. Let's look at when we decrease the temperature. So if I decrease the temperature, I throw it in an ice bath. Now this time I'm taking heat away from the reactants. And since I'm taking heat away from the reactants, the reaction is going to want to compensate for that lack of heat. And think about that heat being a reactant on the left side. Therefore, the reaction is going to shift to the left to where the heat used to be. Otherwise saying that I'm going to end up having more dinitrogen tetraoxide than I will nitric oxide on the right-hand side. And you can think about it this way as well. I slow down the collision between the molecules. Therefore, I will have less of the N2O4 break apart to make the NO2. Therefore, the reaction is going to favor the reactant's side. So you can imagine that this is flipped if I've got an exothermic process. If I've got an exothermic process, you will have the reactants shift to, or the equilibrium shift to the side where the heat is not supplied.